So I want to talk about the shapes of molecules. And in order to talk about the shapes of molecules, they use a theory. It's abbreviated as VSEPR, which is an acronym for valence shell electron pair repulsion theory. And so the basic idea is like charges repel. So if I have two electrons that have negative charges, they will repel from each other. The way we typically do Lewis structures is you'll have a central atom, showing here as a central element A, and then you'll have peripheral atoms or things attached to it. And so the basic idea is those things will get as far away from each other as possible. For instance, if I had just two things, right? So here's a central atom, and then I have another atom, and then let's say it's another atom here. And then these two atoms have electron clouds. How far will they get away from each other? They want to be bonded to the central atom, but they're going to repel. So they're going to try and get away from each other. And so all VSEPR says is they'll try and get as far away from each other as possible, right? So this one's going to move that way, and that one's going to move that way. How far apart could they get? What's the maximum distance they can get away from each other? So at the end of the day, they would be able to, in this particular case, they would be able to get 180 degrees away from each other, right? That's the situation here. And so that's what they'll do. What we'll also see is that if we have a pair of electrons on the central atom, so I'll just imagine a p orbital sticking off of one side, and there's some electrons in there, those will also repel. So if the atom tries to get too close to that pair, it will repel away from that p orbital as well. So you need three atoms to have a bond angle, right? Showing here in this diagram that I made, you need to have a vertex and two rays to have an angle. If there's two atoms, the shape is always the same. How about oxygen? Let's say it's double bonded to an oxygen atom, right? That's our Lewis structure. They each have two pairs. So what's the shape of that molecule going to be?
Linear?
Yeah, linear. There's no angle. I can't have an angle. So if there's two atoms, then the shape is always linear. They call this the trivial linear. There are some other linear cases, but this case is just linear because that's the only thing it can be. There's no angles. Okay, so for this atom, this is technically an angle, or this one where it didn't fully fly apart, there's an angle there. But with this one, there's no angle. To say is that the Lewis structure is not the shape, but you get the shape from the information in the Lewis structure. And so what you do is you analyze your Lewis structure, and the central element's given the A, and any substituent atom is given an X. For the X, it doesn't matter how many bonds, single bond, double, and the maximum we saw we could have is a triple bond. Whether it's a double, single, or a triple bond, it's just an atom bond created. Single, double, or triple is the same. And for electron pairs, they only count on the central atom. The substituent atom is given an X. Whether it's a single bond, a double bond, or triple bond, those are the same. So what we want to do is we want to try to assign an AXE situation to an atom. So what you want to do is, one, assign an AXE configuration. And then the second thing you do, the AXE gives you the shape. So this is NH3. They're showing the Lewis structure here. Well, the nitrogen atom's the central, so that's given the A. That's the central substituent. And then there's three hydrogen atoms. So there's three X's. And so we use a subscript, kind of like a formula. And there's one lone pair on the central atom. So this one is AX3E1. You could also just call this AXE. You don't have to show the one. The one is not necessary. So that's showing assigning an AXE configuration. When you have four things around a central atom, the classification is called tetrahedral. So it's kind of like it's like a pyramid, but with a triangular base. That's what they're showing. The methane, CH4, actually has four atoms. So its AXE is AX4, which is tetrahedral. For the electronic geometry, both the methane and the ammonia have four things connected to the central atom. So they're both in the tetrahedral family geometry. The methane is tetrahedral because they're all atoms. So there's a space occupied by each one. Whereas for the ammonia, the fourth item is a lone pair on the central atom. And so that lone pair is technically part of the atom. There's empty space, so to speak, on the top of the nitrogen. So this is a special case. So in the tetrahedral family, you can, if they're all atoms, you get tetrahedral. If we remove one of the atoms from the tetrahedral family, you get trigonal pyramidal. So if I ignore the lone pair on the top, technically the trigonal pyramidal has a central atom on the top, and then because of the lone pair, the other atoms are all below. And technically, also we should talk about you'll notice there's a wedgie here on the ammonia. And so the wedgie means that the atom is coming out of the plane of the board. It's coming out toward us, like yaw. And then they're also showing a dashy back here. And the dashy means that the atom is behind the plane of the board. And so that lone pair on top is repelling. And so it's kind of like a squatty pyramid, whereas the tetrahedral is a tall pyramid, the trigonal pyramidal is a kind of a squatty pyramid. If we do water, H2O, the Lewis structure for water, okay, so in this case, we have two lone pairs on the central atom and two atoms. So there's two X's. The oxygen is the central atom. There's the two X's for each of the hydrogen atoms and the two E's for each of the lone pairs. So this is also four things. So this has a tetrahedral family geometry, but now lone pairs are taking up two of the places in the tetrahedral. So this has a simple bent shape. So if I ignore the lone pairs as shown in the drawing, then I can prop this molecule up on its side, then it has a bent geometry. If I put both of the hydrogens in the plane of the board, so in the drawing, they're showing one hydrogen coming out of the plane of the board, one hydrogen behind the plane, and the lone pairs are in the plane. But here, where I show both of the hydrogens in the plane, technically there's a lone pair coming out of the plane straight at me, and there's one lone pair going behind me. But again, they're inside the oxygen atom. So they repel the atoms, but they don't contribute to the geometry. So this shape is just simply bent. So water is a bent molecule. So we had this first classification was the tetrahedral family. There's three cases of tetrahedral, right? So you have if they're all atoms, you get just tetrahedral. And that was, the example was methane. If you get three atoms and one lone pair, then you get the trigonal pyramidal. It's still in the tetrahedral family. You still have four things repelling. There's four things tetrahedrally in space, but the lone pair is technically inside the atom. And then the third case was the bent with the water molecule. So two of the things are lone pairs that don't contribute to the geometry. Okay, so the next classification is if I have three things attached to the central atom. And so a good example for that is boron trihydride, where I have three single bonds. And the boron is electron deficient, so it's missing a lone pair. If you remember, boron only is in the group 3A. It only has 3 electrons. And so for this one, this family, if I have three things attached to a central atom, the bond angles are 120 degrees, and it's called trigonal planar, is the family geometry. So if I think about a circle, 360 degrees, that's shown down here. If I cut it into 3 wedges, each wedge would be 120 degrees. That's the furthest I can get three things apart from each other. Another example would be formaldehyde. So in this case, I have 2 single bonds to hydrogen and a double bond to the oxygen. And so the double bond to the oxygen, still spatially, electron pairs are between the carbon and the oxygen. So it's going to repel just the same as if it was a single bond. So both of these cases are trigonal planar. They have 3 atoms. Both the boron trihydride and the formaldehyde, or the CH2O, have an electronic geometry of trigonal planar and a molecular geometry of trigonal planar. There is another possibility to this, which is sulfur dioxide. And the sulfur dioxide shown in this drawing is actually with an expanded octet, can have three things, right? I have a lone pair and two atoms. So it's still in the trigonal planar electronic geometry. These three electron groups are repelling away from each other as far away as they can get, which is 120 degrees. But one of them is a lone pair. So again, if I ignore the lone pair, I get a bent geometry. And this is a different bent. The other bent was based on the tetrahedral with the water. This one is, you can just think of it as bent further. It's bent 120 degrees. So again, we'll do a little draw. So if I ignore the lone pair, we get bent with 120 because it's based on the trigonal planar. So the next case is where we have two atoms outside. So carbon dioxide is a perfect case of that. So if I have two atoms and there's no lone pairs on the central atom, so I don't care about these lone pairs on the oxygens outside. They're just part of an oxygen's cloud, right? That whole oxygen with its lone pairs is going to repel from that other oxygen. And so again, if we only have two atoms, the furthest they can get away is 180 degrees. And so this is a linear electronic geometry that is non-trivial, right? It's an actual bond angle caused by repulsion. And in this case, they're both atoms, so it's also the molecular geometry. And so for this one, doesn't have another case, right? If I remove one of the atoms, then I will only have two atoms left, and I would go to that trivial linear case. So those are the normal cases. So this one's just like formaldehyde, essentially. Right? I have three atoms, right? And so we decided that there's a double bond. I guess they're doing the formal structures was to argue that fluorine will not have a double bond. When we did our Lewis structure the way we learned it, we would come up with the one on the left where oxygen has the double bond because it only started with 6 valence electrons, right? But at any rate, what will we assign to this one? What would the shape of this be? How many atoms?
3.
3. Are there any lone pairs on the central atom?
No.
No.
So it's trigonal planar?
It's trigonal planar. So that's it. How about PBr3? We'll say, okay, I got 3 atoms outside. Is it trigonal planar? Okay, let's look at the Lewis structure.
It's bent.
Well, I have 3 atoms. Can I have bent with 3 atoms?
Oh, no, it's 2.
So let's try to assign it. The phosphorus is the central atom. How many outside atoms do I have?
3.
Okay, so the AX3. Do I have a central lone pair? Or how many lone pairs? I have 1 lone pair. So I'll just say E. So AX3E has how many total things?
4.
4. So what's the family geometry then?
Tetrahedral.
Tetrahedral. Is the molecule tetrahedral though?
It's trigonal pyramidal.
Trigonal pyramidal. So that's this AX3E is going to be trigonal pyramidal. Aha, CH3SH. What's going on here? So this one, after doing the Lewis structure, we get this. So what's the central atom here?
Carbon.
Carbon, yeah, carbon's actually one of the central atoms. In this case, this one has 2 central atoms. So that means two geometries.
So is it carbon and sulfur?
Yeah, carbon and sulfur. So therefore, what I'm going to do is number 1, I'm going to find carbon. And then number 2, I'm going to find sulfur's geometry. So let's do an analysis up here if I can. Okay, so first, let's look at carbon. How many atoms are attached to carbon?
4.
So AX4, are there any lone pairs on carbon?
No.
Okay, so carbon's AX4. What about sulfur?
Maybe 2.
Yeah, there's 2 atoms. So if we call sulfur the central atom, it has 2. How many lone pairs are on sulfur?
1.
Well, actually, I see 2 lone pairs. So I would call that E2. Each 2 dots makes a pair. Okay, so what's the geometry of the carbon then?
Tetrahedral.
Tetrahedral. And so sulfur's in the tetrahedral family, but it's not tetrahedral.
It's bent.
It's bent. Good. So And when you combine geometries, I don't have a name for tetrahedral combined with bent. So what you do is you just say it's tetrahedral at the carbon, it's bent at the sulfur. Okay, yeah. So if you can see the carbon, this diagram on the right here, the carbon central, you have a hydrogen coming out of the plane of the board, a hydrogen going behind, and then the sulfur and the hydrogen on the hydrogen above and the sulfur to the right are in the plane of the board. So yeah, so you have tetrahedral and bent. So this one's an ion. Here's the Lewis structure. What would the shape of that be? What would the assignment be for that? How many atoms are bonded to the arsenic?
4.
So it'd be AX4. Are there any lone pairs on the arsenic?
No.
No.
Okay, so the shape would then be
Tetrahedral.
Tetra.
tetrahedral. Okay.